welcome you all. Thank you all for coming. I know that this session is going to be hard because you're just after the lunch break. So I'll do my best in order to keep this session interactive. You will see some kind of data flows. I will ask you some kind of questions. You can answer them. I wouldn't like to answer them myself because it's a good way of thinking for you, how we achieve this. This talk is going to be a little bit different than the ones that we've heard during this conference, mainly because this talk is about war stories. If you do like the stories from production, this is for you. If not, if you would like to hear about some more theoretical things, this talk is probably not for you. So I won't be mad if you leave then, because there might be other more interesting talks for you, because this is mainly about how we achieved our deployments, what kind of algorithms did we use, why did we choose them, and what were the problems. So, first of all, who am I? My name is Piotr Guzik. I'm working at Allegro, which is quite a fancy company. You could go to our booth today because we're sponsors also. I highly favor you to do that. I'm also a trainer. I perform trainings for the Getting Data company. This is my Twitter. And this talk is coming from me because I do have some data science flavor. I always kind of like maths. And I will show you how simple statistics, this is why simplicity is on the topic of this talk, why simple statistics might work in quite a robust environment. So, first of all, if we want to start any kind of project, we have to answer the most difficult question, why are we doing it? And I hope that the answer is not that the management wanted something, but that we have some kind of interest in what we're doing. So this is the first question for you. Nowadays, we're living in a world of applications which are being monitored, and it is rather not the case when the application fails and the users are notifying developers that their application has fallen. If you're in this kind of situation, I'm sorry for you, but this is probably not the case in many companies. But what about the data? What do you think? Do we really treat the data as a first-class citizen? Who among you thinks that the company can survive with losing all of its data? What should happen then? What if the company loses their data? Would it operate the same? Probably no. So as you can see, usage of the data is crucial for the companies, but unfortunately, not most of very few companies think about it this way, right? So that losing the data is their problem. But they believe that losing the application in a production, leaving some SLA down, is a huge problem, right? There are many talks when people say that you have to be 100% uptime, 99 and 5/9% of uptime, but not many people will tell you that the data also have some kind of a service level agreement and that you should gather the data, monitor if you gather the data with a good quality, and whether you could do something useful with those data. So this is the first point. We believed that we have to detect some kind of anomalies in a clickstream, because this talk will be about clickstream. Do you know what is a clickstream? Okay, I will explain in a second. So a clickstream is, in general, users' behavior and users' activity that is being gathered on a web pages. When you visit a page and you buy something, or you look at the recommendations, or you want to change the address of where the package is going to be sent, this is your activity. And most of the companies do track this kind of activity. Sorry for that, but we are gathering this kind of insights as most companies. And those are the crucial data, because this is your behavior. We can serve better ads for you, we can do recommendations for you, we can profile our services better so that you know that you're using this kind of service which is personal for you and not for general people, right? So in order to perform such operations, we have to treat data as a first-class citizen. And you, as a developer, should be the first one to know that something went wrong. As I explained, nowadays developers do know that the application is not working on production, but very few developers know that they are not sending data somewhere or the data is being lost. And this is why the first quote come in, that nowadays we're in such a strange situation because we're engineers, don't forget that. And in 20th century, engineers did make a few mistakes. If they built a wall, it could not be 90%, it could be 88, 87, but those mistakes were general minor mistakes. But in IT world nowadays, engineers make crucial mistakes. I'm not sure, have you heard about GitLab, their dropout of production DB? This kind of mistake was not possible where you had mechanical engineers, builders and other kind of classical engineering. There were no such mistakes because everything was counted, measured, and everything seemed to work fine. Whereas in IT world, there are spectacular mistakes, and we have to keep up. We have to protect ourselves from such mistakes. So, what was our motivation? First of all, we have to know when we lose the data from our production system so that we cannot serve better ads, recommendations, and other things. Well, we thought that losing data is somewhat similar to losing the money because, for example, if you charge some kind of companies for displaying their ads and they're displaying the ads for the people that don't want to see them, probably you're losing money, right? Because you do not do what you were supposed to do. And from the technical point of view, we came to the idea that this should be a monitoring system so that the team who is responsible for coding, gathering data from components of the web page gets notified when those data is being lost, okay? You can think of it this way. You've got the search box, and it is very crucial what is being, what do people search, right? What's the most common typos in searches so that you could fix them, because Polish language is quite difficult, and you could try to fix something automatically. You could think what the users want from that perspective. So if the search box is losing the data, we're losing the money, and we should notify the team that's being responsible for search box immediately that, okay, your search box is working, it's working really good, but you do not gather the data. So this is not exactly what we want, okay? Although the service might work, it might not gather all of the data, especially in the microservices environment, where most companies now try to be there, but they do not know that the data flows in microservices are really, really hard. It's not that easy so that you have 1 DB under the hood and you could gather everything, especially when you do something like a clickstream. So, those are the questions that we had to answer before starting the project. First of all, how to gather the data. Where should we gather the data from, and what should we look at? Then, should it really be a real-time anomaly detection? Is it okay if we have 1 minute delay, or maybe 5 minutes delay are still okay because it's a monitoring, right? We would like to call someone on the duty from the technical services that they are observing in order to fix it. So probably this should be near real time, because you wouldn't like to call someone in the night after 2 minutes of disruption because it might be an error in measurement. But if the box is not performing, let's say, for 10 minutes, it's okay. The automat could pick a phone and call him in order to fix it. So near real time should be okay. And what is the acceptable delay, right? Because from the moment that you gather the data, there are late events. The events may occur, may get lost somewhere in the network. They might get reconnected. So you should also think more or less about the delay. For how long could you wait for the data before you check if it's okay? And last but not least, the most important domain question in here, what actually is an anomaly, right? Because there are a lot of papers, a lot of white papers, but none of them really tells you in your kind of domain what is an anomaly. So, some technical point of view, we decided that we're going to use Druid.io. Who amongst you have heard about Druid? Okay, and today, if we have enough time, I will perform some kind of a demo of a Druid, because I believe this kind of technology will change the way we think about gathering the data in the future. What is a Druid? Druid is an OLAP engine. Do you believe that you could perform OLAP queries, like, the data warehousing and all of this heavy stuff in real time? Who amongst you believe that you could have OLAP cubes built in real time? Okay, so I hope we'll manage to get to the demo today so that I can show you that actually we can, nowadays, get a data warehouse working in a real time. And this is what we needed, right? Because we want to aggregate data in, let's say, every 15 minutes, right? So that 15 minutes is still fair enough in order to call someone on duty to fix their issues, right? it's acceptable. If you do it eagerly, probably there will be more false positives, and this is what we do not want, because we will be calling up people in the night in order to fix their systems. So false positives are bad in here. We would rather would like to be liberal in the way we work with the other people, because it's people and not the machines. And what should be measured? That's also the very important question before you start developing such a detector or machine learning. You have to measure some values that would be evaluated. What's the answer that you want to get? How much is okay? How much is not okay? Where are the problems? What are the differences that are still acceptable, okay, in what you got? So the measure, we thought about that. We're not data scientists, we're simple engineers. So we want to create simple things, not some fancy algorithms. I'll go to that in a minute. So we decided to go with the simplest counts of what we are measuring. So what is the core data in the system that we're talking about? If you could see this pseudo SQL code, this is more or less what we want to perform. And for example, we're counting how many events from the web page were gathered in specific category and actions of the users, let's say in some kind of time window operations, here 15 minutes. And example, we're working on a page views, so that you click new page, go to the another page, there are referrals between them, the links, so that we keep tracking what the users are doing. So, for example, here in this query, we would like to know how many were the search boxes interactions and which of them led to the show item. If you do, show item is generally the auction, the bidding, right? The way you go to the product, so in order that you could buy it. So this is the simplest count that we could think of. And it's a classical all-up cube query because it got a group by clause, so that we're not interested in single events, because single events are not of interest. We only measure some kind of statistics in order to know if system is performing okay. And this is the first look at our data. And here the question for you, could you see any kind of anomalies here? This is the result of the query that I showed you a few minutes ago. Are there any anomalies here? There are no anomalies, okay. Anybody sees any kind of anomaly? Where? First and second day. Okay, to be honest, I can tell you that there are 3 anomalies in here. The first one is in the first day, this peak of the load. This probably is some kind of anomaly, because as you can see during the daytime, the load is as big as in the night, as in the evening. This is rather unusual, because people are at work. Okay, so this shouldn't look like this. Also, the second day is, there are 2 anomalies. One of them is a peak in the load, and the second one is a dropout. Not knowing why, okay, people didn't interact with our system for a short time of period, and there's a dropout, okay? You could see it here. Not sure if, do you see this? Okay, so this is how few human thinks, okay? This is what we believe in when we look at it, and the rest of the curve of the system looks perfectly fine, right? So now that we know the data, we have to look at it once again and answer some simple questions. So please, look at it and think of it, what can you guess from this data? Is it okay to compare day to day? No, why? Yes, perfectly fine. That's the correct answer. You cannot compare day to day, okay? Because people in general uses the system in a weekend rather than during the working week. So the load is heavier. So you cannot compare Friday to Saturday or Saturday to Wednesday because those are totally different numbers. What else can you see here? So what is the period? Is this data more or less periodical? What do you think? Yes, and what's the period? Many periods, but the smallest unit of time that is a period in here? A week. Cool enough. Good intuition. And do you see anything else that might be useful while building an algorithm? Anybody? Okay, so I will show you a few things. What we can guess. Clickstream is rather a periodical system. A period is a week, definitely not a day. You cannot compare day to day. And last thing that you should notice in here, and I will show it once again, please look at the early morning and the end of the day. The curve is getting, its load is getting really high and really low in a few minutes, right? It's a huge dropout and there's a huge increase in the morning. So that you should be aware that your system should manage it somehow so that the rapid growth of the data and the rapid loss of a data is not a problem, okay? Because it may not be obvious, but if you look at the curve somewhere here, so that there's a dropout, and here the data is being gathered rather in a bigger amounts, this should still be okay in our system, okay? This should not be treated as an anomaly, so that there are some big impacts in load. So, now that we know basics of the data, this is the way that we have always worked with the data, and I encourage you to do the same. Look at it, try to guess something, try to find some things that are common, so that your algorithm might be a bit smarter, if you obviously want to create a handcraft algorithm. So, we came to the idea that what should be the best algorithm and the best code. And the answer is obvious. The best code is the one that you do not have to write, so that it's already there. So as good engineers, we wanted to check if there are some libraries that could do such operations as guessing if there are anomalies or not, could be taken from GitHub or somewhere else. And obviously, there are some kind of frameworks. We tried the Twitter library, which didn't work out for us, because there's a heavy math beneath the hood. I will repeat it once again. We're not the data scientists. We wanted a simple solution so that the Twitter library with this heavy math wasn't okay because we didn't understand the outputs. We wanted a system that's a monitoring system. We want to show it to the people so that they could look at it and know in 2 minutes, okay, this is fine, this is not fine, this is an anomaly. We didn't want it any kind of a sophisticated system, very difficult, so that people should look at and, the system called me in the night. I do not know if it's an anomaly or not because some kind of neural network system decided to call me. We didn't want it because there's a people-to-people interaction in there. So we decided that we need something different. And there are very interesting algorithms called HTM algorithms. They're based on neural networks. There are a lot of increase in interest in GitHub using HTM algorithms, but they are way too hard. We tried them. For example, we changed the size of the vectors that are used to train neural networks from 32 bytes to 64 bytes, and the results changed no matter why. Okay, the results were totally different. We didn't understand why, so it was no go for us. Because if you do not understand the system, you cannot maintain it, and you cannot say that this is your system, okay? So the decision was that the solution must be easy. The easiest solutions are the best one. That's my belief. So that we will create a simple model. And right now, we know some basic facts, what the simple model should be. So, a perfect model that should work with detecting anomalies should be simple. This is the most important part. Must be time-aware, because this is a time series data, so it's got to know something about the time. Detection should be performed rather in minutes than in hours, okay? Because if the system is not working for an hour, it's too much, but a minute might be still okay. It should adapt to the trends, so that there are some popular items. Not sure if you heard of fidget spinners. This is a typical trend in anomaly detection, so that at the beginning, when people type it, it's an anomaly, but after some time, it's a trend, okay? It's just trending. Some kind of ads, good ads, make these situations occur, so that there's some really good ad, and people click at some things, and at the beginning, it should be an anomaly, but after a little longer period, it's perfectly okay. So that the ad made an interest and people are looking for something. So it should adapt to trends. It should not report too many false positives. Do you understand why? Okay, not to call people, cool. That was our goal because they're our friends from the company and you know it's kind of a stupid idea to call your friend from company in the middle of the night just because some kind of a system decided to. And we decided that the simplest mathematical concept that could perform anomaly detection is called confidence intervals. I will show you in a minute what was the scratch, the draft of our algorithm and why we decided to go with it. By the way, if you are interested in developing some kind of algorithms, this is the most sophisticated tool that you can use. Absolutely the best one. We tried a few, but none of them worked as well as the whiteboard, the classical way of working. And it was really good because we had hot discussions down there, like in a class. Back to the high school, there was a hot discussions under the hood, and you could draw something, which is not that easy when you think of coding something in a system. And this is the draft of the model that we wanted to create. So, the green line is an actual traffic, actual web traffic. The yellow line is the prediction, what we expect, how it should behave. And the orange line is the lowest possible amount of traffic that is still acceptable. And the blue, or teal, if I can tell you, because I checked how it's called in English, it's a teal color. This one tells you that it's the highest amount of load that is being treated as an acceptable, okay? These are the confidence intervals, very simple to look at. If you present it to a typical developer, he may not call it orange and teal, but he'll get it. What's the decision of the algorithm, whether it's an anomaly or not, okay? So do you still think that this is simple enough? Okay. So now we did our first coding. I call it first attempt in learning. It's an acronym. It was the first code that was a statistical model coded in R. It wasn't that bad at all. Here's the results. The red dots are saying that this is not an anomaly, whereas the blue dots says that it is an anomaly. And as the first algorithm is not that bad, it did find out the anomalies on the September of 26th, but there were some issues. Do you know where are the issues?
There's a bunch of false alarms.
Yes, there are a lot of false alarms in this growing and rapid growth and rapid loss of the traffic in the morning, which is the worst case scenario because the worst kind of idea is to call someone in the morning, and this algorithm would do that. So we looked at it, and the answer was that it led to overfitting. The biggest problem with machine learning algorithms occurs when it led to overfitting, so that it's very narrow measurement errors, and it's an overfitted algorithm. And this algorithm led to overfitting the trend, so that the rapid growths and impacts led to false positives. But it was our first attempt in learning. And the experiment in progress, we were developing more and more. Now we're sure that trending is just a little bit important. Trends should not change the way we think about the data, because there are only short times when trends appear and trending data. And now something obvious. What about outliers? We thought, come on, it's our system. There are some kind of retries, but there shouldn't be too many outliers, okay? Because this is what outliers are leading for when you come to the statistics. If you do have outliers in your data, you will have such a big peaks of those confidence intervals so that nothing will get to the anomaly, okay? This is very important to get rid of outliers, mainly to the standard deviation problem, if you think of it and reason. And thankfully to that we know now that duplicates are a big problem, we could think, why do we have duplicates? Then it came obvious. If you're working with the Kafka and HDFS, you have to dump data from Kafka to HDFS somehow. That's our problem. And most of the tools that are available as a free software do it in a way of at least once, so that they give you a guarantee that you will never lose the data, but there might be some duplicates, okay? If something gets stuck, you might get duplicates on the HDFS, which is our storage for the historical data for this system, and this was our case, okay? So another thought, a great way to deal with the outliers is to work with the percentiles. 99th percentile of the data is a great duplication removal, okay? It's one of the best things that we've gone, so that the outliers might be for, say, 2% or 3%, then 97th is still okay, and it will let you get rid of most of the outliers so that you do not see such things in your models. So, now that it started to work a bit, we came to a very sad conclusion. We've coded something in R, and we're not data scientists, and who amongst you know R language? The same was in our team, not too many of us. And as we're working in Allegro, we have some tough decisions to make because we cannot go to the production if we do not monitor our system, if we do not have the automatic deployments. And it was almost impossible to achieve it with R. So, because we didn't know R so well, it was very difficult to deploy it, to monitor it, which is very important. Monitoring is one of the core things that you should do with your systems. So a very sad decision. We have to rewrite what we've started from scratch, because now we do have some knowledge what should be the model and what are the data, and we should do it in some kind of a language that is being acceptable for the JVM engineers. We decided to go with the Scala because most of our code base is written in Scala. So this is the very simple input that's coming up from Druid, which I will show you in a minute. Do you see this code, or is it too small? Okay, perfect. So, what is the model key, okay? What is how the data gets aggregated, because that's important for you to understand our decision. If you look at it, please tell me, what's the aggregation model for this kind of data? Anyone? Count per day. Close, close, close. If it's per day, there shouldn't be hour of the day and minute of an hour. It's count per minute, okay? It's count per minute in these group by clause. Do you remember it? Or shall I come to the slide once again? I will show it once again so that you understand. So the model that's being coded in Scala is count per minute that's being shown in some kind of dimensions. And dimensions is this: category, action, and a minute. Okay? Those category and action here are dimensions. For example, there will be multiple, the Cartesian thing from those dimensions. For example, or searches and show items. These are the pairs of the dimensions that we're talking about. Clear? Right now? More or less, what's that? Perfect. So, this is the very simple input to our system. And generally speaking, this is the whole model. Not too much, as you can think of it. And now we came to I will try to show you what's the math behind the hood. Do you know the EEMA function? Have you ever heard about EEMA? Okay, so now I will show you something. Have you heard about mean? What is the typical problem with mean? Let's look at it, because we started with something very simple like median and mean, and we came to this sad problem. Can you see what might go wrong if you use very simple metrics over the time for the time series data in such a situation that this is what the data looked like, okay? Can you see something? No, this data is okay. There are no anomalies in here, okay? This data were perfectly fine. But can you guess what might go wrong? So the problem is that if your algorithm learns how it should work in this period of time, and then it gets operated in this period of time, everything will be treated as an anomaly, right? The simplest math like mean or median cannot cope with it, but there are some nice mathematical functions. One of them is EEMA, which is very simple, and I will explain it in a second. It's called exponential mean average, okay? If you would like to read about it, there are nice video tutorials on YouTube. It's what bankers love, because it's the way that it's calculating the mean in some kind of a time window, okay? This window is sliding over the data, and it's got the head, as in the code, okay? Please look at the EEMA function. It's take the current thing that it's calculated, the newest value, and how big is the impact of the new value based to the given value, okay? So that it forgets. The most important thing with functions that are operating in a window is that the fact that they must forget what they've already learned, because the data might change over time. If you want to perform streaming machine learning, I repeat once again, streaming, not classical batch machine learning where you have training sets and other data sets, but streaming way, you have to forget what you have already learned in order to perform all the time okay. And EEMA function takes the weight so that the newest samples are important and the older samples should be forgotten, okay? Because if we think from the business perspective, this is exactly what we want. It is more important for us how many users are searching something on our platform right now than how many users were searching on our platform a week ago, okay? We should think how many users were there 1 week ago, but for example, this should be 10% of our model, okay? And how many users were looking for something 2 weeks ago should be, for example, 1%, okay? Because this is a far, far history. It shouldn't be the most important thing in an algorithm. So this is the exponential means that the new data are important, are more and more important, where the data that comes from the history are getting less and less important, okay? Have you got some kind of idea what I've talked about? Okay, cool enough. So we decided to go with the EEMA. This is the answer why. Because we want to roll, okay? We want to roll so that if the load is getting heavier, it will get into this time window, and when it's there, those samples will get important, okay? Those will get less, so that for a short time, it will be treated as an anomaly, but in longer periods, it will look perfectly fine as a trend, okay? And we've coded it. This is more or less the whole algorithm for anomaly detection. We're getting the real value, we're creating a model, we're calculating the prediction, we're calculating the lower and upper bound, okay? You know what is the lower or upper bound, these two lines. And then we got the mean of the model so that we know how in the future to cut this exponential mean average. And the decision is very simple. An anomaly is whether the data is below the lower bound or higher than the upper bound. So it's a really, really simple algorithm. But we didn't come up with the last problem. We deployed it to production. It was a huge success. But we missed something, and we couldn't invent it. That's why I highly encourage you to go to the production as quickly as possible, because only when you are in a production you will see some real behaviors, not the one that you only thought about. And this is one of them. There are deployments. People do deploy the new versions of their components, and one of the deployments made such impact on the system that their loads, as you can see, got bigger, and it stayed that way, okay? And our algorithm wasn't able to cope with those anomalies because it couldn't learn anomalies, okay? If you want to detect anomalies, you cannot look at them and learn that those anomalies are in your data set. You have to eliminate them and mark them as anomalies. So our system wasn't able to do that because we didn't think of it that there might be some heavy deployments that people will love and use those components twice the same as they used to, okay? But it happens in a real time. and we have to manage it. So here you've got the nice graph below that this is not an anomaly, no, 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 no. And here we've got definitely an anomaly, okay? This is what the computer see. And there are thresholds whether to call someone or not. So the last idea behind this algorithm, we should go with the probability that this is the anomaly, because that's what the people do, okay? You look at something and say, this is an anomaly, and I can tell you that this is an anomaly with 99% of sure. We should call someone then. But if you look at it, this might be an anomaly, but I'm only 30% sure that this is an anomaly. You better leave it this way, okay? And that's what our algorithm do. And what's important, it's with sign. Because when people click more than they used to, it's okay. It's still an anomaly, and someone should look at it, whether there are duplicates in data or something like that, but it's okay. But we should be extremely cautious when it comes to the drops in data, because this is rather important for monitoring, whether the data gets lost, okay? And if you got the anomaly with the sign, so that -1 means that there are no data, it's a better way to cope with it, because then you could have stricter policies on what to do if you're losing data and what to do if you're gaining data, okay? This is the reason. So we fixed that. We decided that there should be a longer window that's calculating for how long an anomaly that is lasting is becoming something normal. Very simple algorithm. Why? Because if the team that is responsible for some kind of box gets notified and they have the SLA, for example, for 3 hours, they have 3 hours in order to fix something. And if our algorithm, for example, says that after 5 hours of lasting anomaly, this is becoming a norm, it's perfectly okay, because they have only 3 hours. We're still liberal. We've given them 5 hours. If they cannot fix something in 5 hours, we decide that this is actually what is happening right now, and this is the truth, okay? So our system is quite intelligent in this way that it takes how much the team got to fix something, and it's liberal so that if they do not, after long-lasting anomaly occurs, we're deciding that this is not an anomaly anymore, okay? Because that's what people do. If you look at it, it's more or less what people think. Right now, there are no anomalies. Here something has started, and it lasted for a long time. No one has fixed it. So after some time, you should bump up. You should come up to this level and say, okay, from now on, someone has deployed something, and this is the new standard. I should forget what I've already learned. This is the most important takeaway from the streaming machine learning. Now I'm forgetting what I have already known. And I'm starting from this point, and once again, there are new levels, okay? Can you understand what's down there? Okay, still simple? Yes?
What do you mean by we multiply all model parameters? What do you mean by we multiply all model parameters?
Okay, so multiplying model params is a technical thing. In general, you forget what you have already learned. Because now you know that the measurements that were here were not enough. You have to multiply them by some kind of constant, for example, because this is a linear, okay? This should be simple, as I told you. So this is linear by multiplying. You see that all those lines bumped up to some kind of level, okay? This is fair enough if you think of simple counts, because there's a new level of something that shouldn't be anomaly anymore. Okay? And the deployment, we decided to go with a SaaS model so that everyone could deploy the same code base, but with different configurations, okay? So the code was written once, but multiple teams have different configurations of letting them know if something happens. I will show you in a minute how it's done. It's more like this, so that there are a lot of parameters, but they're quite obvious now, if you think what I told you. For example, max anomaly period. What do you think? What's that?
So how long we can survive the peak before we start reloading?
Okay, perfectly. That's the correct definition. And there are others, as you can see. Lower bound, some kind of mathematical exponents so that we can calculate whether it's an anomaly or no. There are not too many parameters to tune. To be honest, there are 5 parameters that people should know what they are putting. And to compare to the Twitter library, whereas there are 32 parameters, I believe this is okay. We have 5 parameters. The simplest library that enables you to do so have 32 parameters. So I believe we're a bit better. And if you look at the query, so that what the team is looking at, if you look at this board, does it ring a bell somewhere? Have you seen something like this today? Anyone? I have showed some kind of pseudo SQL, and this query is more or less coded here. Okay? Nobody is coding SQL queries in this system. They are only declaratively saying that they are interested in service ID, category, and action, especially 2 categories, listing and search, and actions, some kind of listing, items, possible show items, and the metric that is being used should be the event count, okay? Declarative, simple way for developers to decide what they should monitor. It's mapping one-to-one to the pseudo SQL I've shown you before. And generally speaking, that's the basic concept behind this algorithm. That was more model, machine learning stuff without some very fancy algorithm, but the simple way that should work. I hope that you can understand it in a while. Now, well, I like this slide because I believe it's important to say thank you for people who helped me working with these algorithms and other stuff. I have an opportunity. So I do say thank for the people who work with us, helped us. And now I still have some time, so I can show you more technical stuff. How we did it from the technical point of view, from the Druid, what is a Druid. And after that, there will be maybe a small demo if I have time, and Q&A, okay? So that's the end of the algorithm. I believe that the algorithm was quite easy, and it's working, what's cool. And now the database behind it, okay? We decided to go with the Druid.io. It's a quite simple tool. I loved the way that it was developed because there's a company in the US called MetaMarkets, and they did a very pure business on how the ads are performing for Google and other things. And they coded some kind of an OLAP cube engine, and they decided that it's so good that they will open source it, although it's their internal tool. And they did it. It's open source for 3 years, and it's a really nice library. It's battle proven because they were using it on a production for the scale of the Google Ads. So it was really battle proven, and for big queries and for big data, it was well suited. And what's cool, it was open source just because nobody thought that it's a sell and forget issue for our company, but they wanted to share it. And that's why I put this slide, because it's a nice thing to do from the company. What it is, what it's not, and what are the pros and cons of this tool. It's lightning fast. I will show you it in a minute, how it's really blazingly fast in the million of records, and I will explain it why in a second. It's very stable. It's almost rock solid. It's working with us for half a year, and it never dropped. So it's a rock solid system, I can tell you. It's a generic tool. It will accept all of the data as long as you provide some JSON configuration about what you want to read. I will also show it to you. And it's got a built-in Lambda architecture so that you could combine real-time results with historical results. It's also a cool feature. The only cons that it's here, it's got, well, quite sophisticated and difficult architecture, but it's rock solid. And the configuration of what you want to ingest from your data must be known upfront. You cannot decide in a runtime what you want. You have to put it in a JSON files before starting, okay? So this is one of the cons of this system. And now some general concepts. Are you familiar with something called rollup? This is how it worked, because we're getting 1 million of events per day. So as you can think of it, if we were to process 1 million of events in our anomaly detection service, it probably wouldn't work that fast. But thanks to the Druid and the way it's working with a rollup, we only operate, let's say, on 10,000 of rows, because it's performing aggregation at the ingestion time, okay? This is very important and this is very smart. So please look at it. Here we've got the timestamps. The red columns are the dimensions, so the business metrics, some business stuff that you want to look at. And the blue ones are metrics, so what you have gathered. For example, those are the clicks on the ads. 0 indicates that there was only, the ad was shown but it wasn't clicked, whereas 1 indicates that someone clicked on the ad and what is the revenue, what's the price for the click per play, okay? And if you perform this query so that you're grouping by all of the dimensions and supposedly count something like impression is everything, 0 makes impression, 1 makes impression, whereas clicks are only where there was 1, and the revenue of displaying an ad is a sum of all prices with clicks, okay? Quite simple. Then you got a rollup. After such group by queries, you do not have 1 million of rows anymore. You're operating on an aggregate, and this is the way that Druid works. So that now you can see that at this timestamp, this kind of business combination values, mails in USA that were advertised by Google had seen in this 1 minute 1,800 impressions. There were only 25 clicks, and the website should get $25 for that, okay? This is the business value that's being aggregated from the row events. That's our situation because we're gathering row events from the clickstream, and we're really interested in some kind of business metrics, so aggregates. So this is the rolling up. The important thing, once again, to understand that this lets you have 100, maybe 1,000 less number of records, okay? This is cool stuff if you really have big data. So the rule of thumb behind the Druid and general systems, big data is cool, but the smaller data, the faster system, if the data is small enough and gathers some business value, it's perfectly fine. So making data small again should be one of your concerns if you really want to perform operative in a quick way, responsive manner, and that's what the Druid really do under the hood. So, as I mentioned, the data gets aggregated at the ingestion time. You are losing row records, okay? It is impossible from the Druid database to read the row record that this guy clicked it at this timestamp. You will never get it. Only what you give is that the typical user at this website clicked this number of ads, and it should be paid this amount of money, okay? You get the aggregates. That's a different kind of thinking. And something that's not really fine, but it cannot work any differently. You can only query things that you have calculated, okay? If you calculate some aggregate, then you only can calculate the dimensions or measures that are already there. You cannot create something new from the scratch. And that's how you query the data. You've got the group by clause, and you can group by as many columns as you want, and this is one thing. You can perform top-end queries. Do you know what's a top-end query? It's the simplest group by one dimension, and Druid is really smart that if you do have a group by query, for example, from 3 columns, it can try to run 3 top-end queries and combine the results so that, one big query with 3 columns in a group by might take 20 seconds, whereas 3 top-end queries, each of them might take 3 seconds, so you are 2 times faster, okay? And if they run in parallel, you are even faster and faster than typical group by query. And the simplest query is a time series query, so that you're not interested in anything that's grouped, but only the data that occurred in specific timestamps. And there are no joins. You cannot join the data inside Druid. The only way to join the data is to create an all-up cube that has already joined data from the external systems, okay? That's why the queryings are so fast, because there are no joins. But you could live with it, because you have to ingest the data somehow into the Druid, and the way to do it is probably to create some kind of application. It has a complex architecture, but this architecture is rock solid. You are hearing more and more about microservices, and Druid has, for one thing that's common with microservices, that each type of node has single responsibility, okay? That's how it looks like, the last slide with the theory and a quick demo. So, it's a lambda architecture. You have the real-time nodes, and you have the data that are stored somewhere and given by the historical nodes. So there are two types of nodes, real-time nodes and historical nodes. There is a metadata coming around the cluster saying what kind of data are being ingested, what are the dimensions, what were the last query for those data, and this is kept in the coordinator nodes. And the only nodes that the client sees are the broker nodes. So it's a gateway to query the data from the Druid. It is quite complicated architecture, but what's really nice from it is that if some of the nodes comes down, the cluster is still operating, okay? It happened. For example, real-time nodes may fail, but if the real-time nodes fail in Druid, then you won't be able to ingest data from Kafka, but it will be perfectly fine to read the data that was already ingested and to ingest data from HDFS probably. So this kind of design is quite cool. And right now I would like to show you how you can work in a Druid in the simplest fashion. So I will start a Druid application right here. As you can see, all of those nodes are being run at the moment. Then you should run some kind of a Kafka under the hood if you want to load the data into the Druid, so that the Kafka is for the real-time component. Okay, now it's starting. Now I will start some simple application that I've written so that you could see that I am loading the data from the batch and from real-time. Okay, the app is running. So right now we can go to some systems. This will be our UI. This will be the admin console for our cluster. This will be the second admin console so that we know how the cluster is operating and what it's doing at the moment. Now I will execute my batch application. Okay, we have generated a batch data. And right now I will try to load this batch data into the Druid. It will take a while, but it should work perfectly fine as for the demo. So what I've already done, sorry for that. I can run a cluster. So this is starting the indexing of the data from the batch, from the file. It could be a local file, it could be HDFS file, and as if you look at the console right now, this is cool. It's got nice monitoring. The task is running in here. You could see what's the status, what are the dimensions of your data that's being loaded, what are your metrics, from where do you want to load it. So it's really nice for monitoring purposes. Okay, it's finished, it's successful. Now probably we will have to wait about 1 minute before it's loaded into the cluster. Sorry for that, but it's not that good machine, and it's not actually a cluster because it's only my local machine. But after 1 minute, it will occur in here. And you will see that then we can add our data to some kind of UI, and the UI is blazingly fast. Okay? If you want to work with the Druid, you will love these kind of UIs because they are working fast. Okay, so now we have our data source. It's already in there. You could go in here, see what are the dimensions, what are the metrics, and please look at it. The file, the segment of the data inside the Druid, the aggregates, are more or less 1 megabyte, okay? You can see it. Whereas if we go to the file that I've generated, it weighs 33 megabytes, okay? So the same data after aggregation weighs 33 times less. Cool? I believe it's fine. Making data small again, remember. So now we've got the batch data. Now we can load them into the UI. You could see something similar, okay? And now these are the million records under the hood. This is how you can say that, let's look, for example, at the last week of the data. And this data is about shopping. So we can look how different types of shops were selling things, and we're a typical businessman. We're interested in total number of sold items that calculates to the money. And for example, you can look at the line charts, how it's look. It's really blazingly fast for the million records under the hood that's being aggregated into thousands of records, okay? It's a live demo, now it's still working, so cool. And what's even more, if you're not interested in looking at the timeline, then you might take, for example, let's say the category of the shops, and then once again shop names, and you can look how the different categories are being sold inside the shop, different types of shops, okay? Totally cool for me, because what you really want to look at, it's a heat map. So that, for example, if you look what different stores are selling, you have the combinations, right? So that this kind of category is being sold more, there are more sales from this in this type of shops, okay? This is what typically analysts want to get from their SQL queries. And here you can simply click it. So last but not least, I would like to generate some real-time data. This endpoint is producing data to Kafka. And I will show you that after, let's say, a few seconds, you will have real-time indexing service in here. The data is being right now pulled by the Druid from the Kafka. And if we look at the last hour of the data, for example, let's split it by the time. That's the data from the Kafka that I've already produced, okay? If you look at it at the last minute of the data, now they are here. Let's wait, for example, for a second. Now I'm not producing any data, so we will have no data at all. And now we can produce data once again, dump them to the Kafka. Might take, for example, a few seconds, but you should have data somewhere in here. If you look at the biggest period, okay, they are already being produced from the real time from the Kafka. So you could dump the data inside two things. You could look at the data at different perspectives. And what's really, really cool, and why this tool is so good, you could split different things. For example, if you have the category of things that are being sold and the day of the week, it's obvious that some things are being sold better at different days, right? If you're interested in looking in the hierarchy of things, that the category is the main and day of the week is the second, it's okay, but you could swap it. And if you think of it, that this swap took 2 seconds, okay, it took no time, now you can look at it from a different perspective. And if you're interested how the things are being sold in a weekend, it's cool. People buy alcohol during the weekend. It's perfectly fine. You can see it from one click. You do not need to know any fancy SQL. And it's nicely to monitor. You could see what's being run. There's a run. You could see that it's something. Yes, you could know what the cluster is doing. You know that your data sources are in here. How much of the memory do they take? It's really, really nice software. I hope that you enjoy it, and now I will be honored if you have some questions. I will try to answer some of them. So thank you for the presentation, and now it's your time to ask me something. Open source UIs, and there are okay. The UI that I've provided you is a trial. It's not very expensive software, but Druid is open source platform, and there are open source UIs. This one is based on a license, but generally speaking, it has an open source version. It's not a problem. Pivot. Pivot. The name is very good. Do you know pivot tables? More or less, the thing I did during the live demo was pivoting some things, and that's what most analysts do in companies. And it's really blazingly fast. From Airbnb, and what's the name? Superset, yes, we're using Superset. Superset is also an open source UI, but the Superset is not that good at real time. Superset is cool if you want to look at the historical data because it's got better visualizations of, let's say, bars and splits, but pivot is better for real-time data accessing, and superset is cool if you want to have static dashboards, typical reports for business, right? So that this shares 20% of the data, this takes 30, it's cool. And yes, we're using superset. That's the second UI. It's not open sourced yet. It's very simple algorithm. It may go to open source one day. I can't tell you when. We probably will try to do something about it, but unfortunately not yet. But I hope that you can agree with me that it's quite simple, yet working, as I've showed you. There are no magic in there, which is a rare case in anomaly detection algorithms, because most of them do have some magic math under the hood or neural networks. That's the second thing that's very popular, but not so easy. Any other question? Okay, it's not a problem. In Druid, right? We have 2 data centers at Allegro. It is very important to know that the only problem with 2 data centers using Druid is when you think about the real-time technology, because there are 2 ways to import data from the real-time to the Druid. One of them is based on Kafka and component called Tranquility that was run by me, and it supports 2 data centers. And the second one, which is faster and generally better, is called Kafka Indexing Service. And the only flow that it has, it does not support multiple data centers. So depending on what you want, you have 2 options. We're using Tranquility component. It's the older one, more deprecated, but the killer feature for us is what you've asked, a very good question, that does it support multiple data centers? Yes, it does. To be honest, I can show you why. If you want to look at it here, these are the times and the periods of the segments of the data inside Druid, right? Here. And the Tranquility, what it does, it merges from multiple Kafka clusters, one segment, okay? Whereas Kafka Indexing Service is faster yet dumber because it will replace them. So if you have multiple Kafka clusters, it will replace one with the another, so it's not working general in multi-DC. But Tranquility works perfectly fine. I highly encourage you to read some Druid docs. They're quite difficult, to be honest, because it's not that popular framework yet, but the docs are not that bad, okay? You could read, reason about it. It's already there, if you're interested more and more. And it's alive. Commits are there, people are committing, so someone is still using it. And I highly encourage you to give it a try. If you really, really have thousands of records and want to aggregate them in order to perform faster. Any other question?
Okay, let's assume that you detect some anomaly and you call the responsible person at midnight. So what this person has to do? To give you some example, how she has to react.
Okay, this is a bit more difficult insight question. To be honest, the way to cope with such things is first of all to check how your component is behaving. If it's producing a duplicate, we have this kind of metrics if the data gets duplicated, because every row that we're producing has some unique IDs. So if you calculate the count and the unique count of those values, you will already know if you do have a duplicate. So for example, this is one way to go. And the second is to check, obviously, if your system is alive, because then you might produce less and less data. Or if you have deployed the application, let's say, in 16 nodes of a cluster, let's say to check how many of those nodes are still alive, because maybe load balancing is not working perfectly fine. There are multiple ways to deal with it. First of all, check uniqueness, then check how many deployments are alive from the cluster, and if the load balancing is still okay. That should do the trick. Any other question? it looks like this. Our system works this way. We're gathering the data to Kafka, and it's where the data is. But after some time, this data gets dumped into HDFS, and these are the historical data. There might be duplicates there, but those are more or less like the HDFS is more like, could be treated like a database, okay? So these are historical data, the one that will be loaded to the Druid as I did it from the file, okay? This is it. And the second part is the new data that are not yet dumped to the HDFS, but are only on Kafka. Very good question. The answer is that we do, and it's a killer feature of Druid that I haven't mentioned, so that you could replace the data from the real-time with the data from the HDFS. It's good because you could change, for example, the query granularity, yeah? Why? Because if you analyze real-time data from the Kafka, you might be interested in what users do per second, but for example, if the 1 week is away, we're 1 week after that, we could dump the same data and replace them from the HDFS, loading them in such a manner that users can only query it, for example, what users did in 30 minutes. You know, with less query granularity, so that these data weights less, are loader fasted, and are more aggregated. It's even simpler. You've got, as I can show you, if you do not even have to check it, because it's here you've got the data source. And for example, as long as you load something that is like ID, it's not a problem. But a very good question. Yes, Druid enables you to work with multiple query granularities so that you could treat batch data in a different way than real-time data, okay? It's also fancy because, as I mentioned, you could look at the data from the batch processing, for example, in 1 hour granularity, whereas if you're really interested what's going on in your system per second, you could use it in real time. Really cool feature. But very nice question. I liked it a lot. Thank you for that. Okay, so if it's okay, thank you very much. I hope nobody slept after the lunch.